It's my pleasure to introduce Chip Shearer as the next speaker. He got his PhD from the University of Massachusetts, and he is currently at the University of New Mexico. His research interests include planetary basaltic magmatism and the evolution of planetary interiors. He's the head of Apollo's next generation sample analysis consortium, which he's going to talk about right now.
Great, thank you very much. Can you see my screen right now?
Absolutely.
Okay, wonderful. It's very nice to be here representing the ANGSA science team and the JSC Lunar Curation Office. And I'm going to provide you with an overview of the Apollo Next Generation Sample Analysis Initiative, or ANGSA. As many of you all know, between 1969 and 1972, Project Apollo returned over 380 kilograms of material from the lunar surface. These images here provide you with some idea of the different types of materials that were returned. For example, hand samples that were collected by the astronauts that represent different lithologies, from impact to magmatic lithologies, core samples, rake samples, and also what I refer to as special samples. These samples were either collected in unique manners on the lunar surface or were processed in unique manners once they were returned to Earth. What's really important about these samples that I can't emphasize enough is the Apollo samples really strongly influenced our understanding of the moon and the solar system. It provided important chronological data and chemical data for the origin and evolution of the moon, planetary differentiation, and the impact history of the inner solar system, but also the potential dynamics of the outer solar system. The ANGSA initiative is examining 3 different types of samples: unopened, vacuum-sealed Apollo samples that were that these samples were placed within either SESCs, special environmental sample containers shown to your right, or core sample vacuum containers, and sealed, and ideally maintained a Mars-like vacuum on those samples and preserve them. These containers had a sealing mechanism as shown in the bottom right-hand corner, indium seal with a stainless steel knife edge. In addition to these unopened Apollo samples, they are also, the ANGSA initiative is looking at some of the frozen Apollo samples and Apollo samples that were opened, curated, and remain stored in helium versus the traditional nitrogen atmosphere that lunar samples and curation are kept in. The Apollo Next Generation Initiative consists of 9 original teams and over 60 scientists, engineers, and astronauts, both current and former astronauts. My initial concept for this initiative, and it was designed as a new and obviously cheap lunar sample return mission, as these samples have never been analyzed or examined in the past, and essentially processing, conducting preliminary examination, and final analyses utilizing new and improved technologies, and then tying this data into recent mission observations. And finally, the concept of the ANGSA initiative really is linked to engage the very first generation of lunar explorers with future generations of explorers of the moon. Some of the sample goals for this initiative are shown on the left-hand side. overall, we hopefully are investigating the volatile cycle on the moon as recorded by the regolith samples in the core sample vacuum container. Also, there's a joint engineering and science goal that focuses upon how well did these containers work in preserving the lunar record, and what are the implications for future lunar exploration. And then finally, some other science goals, and there are many others depending on the team. How do lunar landslides work in terms of triggering them and their dynamics? And what is the chronology of various lunar events? What I would like to do right now is really focus on the double drive tube sample that was collected during Apollo 17. And the reason why I'm focusing primarily on that is a large number of team members are examining this sample, and we've accomplished the most work on this sample within the COVID-19 environment. 73001 is the lower part of the drive tube. 73002 is the upper part of the drive tube. 002 was extruded from the sealed drive tube, where 73001 is the lower part, still stored in the core sample vacuum container. The site for this collection is Station 3, shown right here on this image of the Taurus Liftrow Valley. It's within a light mantle deposit, and the core penetrates what is a landslide material off the South Massif and penetrates to a depth of a little over 70 centimeters. This study by the ANGSA team is both a continuation of Apollo goals to look at gases that may have been derived from the Lee, Lincoln scarp, but also feeds forward to Artemis because of the unique containment and the unique geology. We're providing a variety of different perspectives in our analysis of these core. For example, placing these members of the team are placing these within the geological context, whether they be surface geological context, surface sample context, or a much broader local and regional context derived from recent orbital data. And this lists some of the team members involved in each of those examinations of the source, the site. The first measurements that were done on this core were done on the 73002, which again is the upper part of the core that was still within the upper part of the double drive tube. This illustrates the advancement in technology that we're utilizing to curate and examine these samples. The diagram, the image on that's labeled 1974 is a simple X-ray image of the same core taken, and the bottom part of the bottom image is a very recent image that we took in November via XCT, and you can see the incredible increase in resolution, which is important for science and examining the dynamics of lunar landslide deposits by being able to analyze grain sizes, but also really important with regards to developing strategies for dissecting the core. In addition to this obvious difference in resolution, the XCT analyses can provide a multitude, thousands of different slices through the core, so we can look at different segments of this core. The core was excuse me, extrude in the de-rind in early November. This is the 73002 core by a processing team at the Johnson Space Center. And this illustrates two of the images of the core before processing. Soon after extrusion, members of our team from the University of Hawaii conducted both multispectral imaging of the core and hyperspectral processing or profiling of the core. And those different reflectance wavelengths are shown in diagram B and C, again, derived from the initial measurements of this core. As we process the core more and more through different levels, we'll be doing additional spectral measurements in addition to the spectral measurements that will be done on 73002. The core in November through end of February was dissected and examined by the curation staff and the PE team. And this just again illustrates the dissection process. And we perform these dissections in a series of passes across the core and essentially collect samples in 0.5 centimeter segments down the core. These segments are sieved into less than 1 millimeter and greater than 1 millimeter grain sizes. And the insert diagram I illustrated here is just some of the lithic fragments collected from one sieving. In addition to just observing the samples and processing the samples, XCT analyses were done on these lithic fragments that were greater than 4 millimeters. And this illustrates the variety of lithic fragment types and textures that are revealed by the XCT imaging. Soon after we released this information to our science team, the University of Notre Dame hopped in very quickly and performed analyses of the crystal size distribution, where they were then able to utilize this data, particularly on the ilmenite from the basalts, to determine crystallization kinetic histories of these basalts. And this will be applied to other lithologies represented by these lithic clasts. Part of the sample was also early on submitted to the NASA Goddard Astrobiology Lab. And this team performed a variety of organic analyses and looked at the distribution and origin of amino acids. And their results will be reported at the fall AGU meeting in a special ANGSA session that will be held at AGU. Another portion of the sample early on was sent and is being analyzed at the University of New Mexico Stable Isotope Lab and the Johnson Space Center Radiogenic Isotope Lab for halogens, hydrogen, chlorine, oxygen, and for a traditional mineralogy petrology study. And the image to the bottom right just illustrates some of our measurements, which are step heating measurements and analyzing the hydrogen content and the hydrogen isotopic composition of the initial sample that we started to analyze. In addition to this processing and analyses, the team is also examining the core sample vacuum container in terms of deciding the best way to open the sample and to collect material or samples from this sealed container. We have already developed a core sample vacuum container strategy, and that has been finalized. and a piercing tool that will be linked to a gas manifold to extract gas from this container will also be an important part of this analysis. And we're doing this because during the Apollo missions, the core sample vacuum containers, which there were two, one collected during Apollo 16 and one collected during Apollo 17, were never analyzed, and a strategy and tools for opening this were never finalized by the Apollo program. Finally, in my last slide, what I just want to illustrate the really important linkage between ANGSA and its link to the Artemis program. As I mentioned, ANGSA is a multi-generational international initiative being run as a sample return mission. Therefore, it trains future generations for sample return missions and really hands off the torch, if you will, from Apollo to Artemis. These unopened Apollo samples, particularly the core sample vacuum container, represents our best chance to evaluate sampling approaches for ANGSA and perhaps also providing additional insights in requirements for handling and processing samples during in situ measurements. And then finally, this is really important in fulfilling the HEOMD specific strategic knowledge gaps that have been kicking around now for the last decade or so. And I think this will provide us an approach for removing some of those knowledge gaps. Thank you very much.
Thank you, Chip. That was a really great talk. And I was so amazed to see how much care was taken when you guys analyzed the core samples. There was some meticulous work going on there. We are running out of time, so I think maybe just one question from David Chevront. Is there any objective to address dust mitigation with this project? Do we have pristine dust samples that preserve physical properties, such as the sharp edge forms? If so, how much?
Could you repeat that one more time? I'm sorry, I didn't hear it all.
Oh, okay. So is there any objective to address dust mitigation with this project? Do we have pristine dust samples that preserve properties such as sharp edge forms? If so, how much?
Yes. What the ANGSA program is trying to do is, again, cover analyses and answer science questions over a fairly limited range. Some of the dust analyses will be done by TEM at the Johnson Space Center, but we are also trying to leave a number of materials and science projects for the overall science community, so that when our documentation is put into a preliminary examination document for the entire planetary community, there will be other science that can be done from these samples.
Thank you.